Hi, thank you for coming to our presentation in which we discuss the use of augmented reality in the context of educational robotics. Educational robotics are a great way for introducing novices to engineering and computer science concepts, as well as engaging more general cognitive social skills, such as problem solving, critical thinking, collaboration, and negotiation. However, imbalanced collaboration is an issue that emerges in these group contexts. This is caused by inequalities in group members' backgrounds, as well as from inabilities to access or share resources. For example, team members who are closer to a computer or who know more about computer programming may tend to dominate that resource at the expense of other team members. Imbalanced collaboration tends to lead to weaker learning, decreased collaboration, and negative attitudes. So, in our research, we investigate how a technology like augmented reality can help this problem. We build on previous research that has shown that when a small group uses augmented reality, this leads to improved learning and permits team members to achieve grounding and balance. Also, in the domain of robotics, it has been used to improve a user's understanding of a robot's state and intent. However, research has not looked at how augmented reality impacts imbalanced collaboration in this context. Augmented reality has several affordances which can make it suitable for this task. For example, by increasing the information accessible to a participant, or by presenting information in the place of action while participants manipulate a physical resource, like a robot. We believe that these affordances make this technology useful for collaboration during robot programming. For this research, we've used this robot. It can be programmed through the USB cable, and it has wheels to move around, and also these small sensors that allow it to sense the real world, such as closeness to objects. Without augmented reality, sensor values can be seen on a computer screen, and users must understand how the computer display maps to the spatial locations of sensors in the real physical world. In contrast with augmented reality, we can see the sensors while looking directly at the robot, and also we can see the identifiers and meaning of each sensor to make it easier to program the robot. Different kinds of information can be displayed through augmented reality, but in this study we only showed sensor bar charts. And students can use this in real time as the robot moves through a maze. Our research questions investigated how the presence of augmented reality visualizations, as well as how the participant proximity to resources, interact with each other to impact variables such as learning gains, collaboration contributions, and equality. We ran a user study involving 40 groups of novice pairs in two conditions, where participants either saw augmented reality or did not. Participants had to solve challenges with the robot, such as having the robot turn right at the first corner or beep when it crosses over the red line, etc. Participants had slightly imbalanced access to resources due to their location in the room, where the computer was closer to the left participant and the robot was closer to the right participant. Although, as you can see in the images on the right, both participants could easily access both resources. In both conditions, participants programmed the robot using a block-based programming interface on the computer. Since people experience novelty effects when first seeing augmented reality, we controlled for this by having both groups wear a Microsoft HoloLens headset, and both groups saw small visualizations on the robot, which just indicated if the program was running or not. One group did not see any sensor visualizations on the robot, but instead saw them on the computer screen, and the other group saw visualizations on the robot, as we have shown before. For our results, on learning, we found that overall, groups experiencing augmented reality, which are colored in red, showed better scores in all dimensions of learning. However, there was an interaction effect, and we found that participants closer to the computer moved the robot more and programmed less with augmented reality, but their learning remained roughly the same between the two conditions. In contrast, for the participants closer to the robot, augmented reality did not significantly affect their engagement with the robot or computer, but they learned much better when they had augmented reality. To understand this more, we analyzed each person's speech contributions to the collaborative process. We find that both the right and left participants increased their grounding contributions when they had augmented reality. And we find that the participants who are closer to the robot did a lot more suggestions to take actions when they had augmented reality. So augmented reality empowers these participants' learning as well as their ability to contribute to the collaboration. Finally, we investigated how participant contributions equalize over time. So here, each graph represents one session and each line is one participant. And we see that in the AR sessions, participants tend to contribute equally over time, while in the non-AR sessions, the sessions are typically driven by one participant more than the other, indicating that AR can have an equalizing effect on participant contributions. So the takeaways from this research are that augmented reality had unequal impacts on learning, depending on participant roles and information access. It was helpful for participants who lacked information and who were focused on performing physical tasks with the robot, but it was not helpful for the participants closer to the computer. However, AR improved grounding and equalized contributions between participants. Reflecting on the affordances of augmented reality, the study findings suggest that when a user had more information available to them, they benefited. But when information was tied to physical objects, this was not useful for the computer user, who could access this information either on the computer screen or on the robot, depending on the study condition. Future research should investigate how these benefits transfer to other contexts. And also in the paper, we discuss how these effects may be achieved using lower cost technologies, such as shared screens or small displays attached to objects. And we compared the limitations of these technologies in comparison to augmented reality. Before concluding, I would like to acknowledge the hardworking research assistants and Harvard facilities that have assisted with this project. Thank you, and I look forward to any questions that you might have.